Welcome back. In the last lecture, we were attempting to find out an estimate of how many lattice points are there inside a ball of radius r, and towards that end what we have seen is that we have introduced function capital phi epsilon for epsilon positive to be indicator function of 1 minus epsilon by 2 b, which means we are shrinking the ball by the radius, keeping the center fixed at 0, and the radius is being reduced to 1 minus epsilon by 2 instead of 1. It is a smaller ball, and psi epsilon we are defining to be the centered at 0 and radius is slightly bigger than 1 convolved with function phi epsilon. So, it is easy to see that if we take, let us see how does it look. This is going to be integral over r n and then chi of 1 minus epsilon by 2 b of x minus of y, and then this is phi epsilon of y dy, going to be then the support of is going to be set of all x such that mod of x by epsilon is less than half. This is nothing but set of all x such that mod of x is less than epsilon by 2. That is what the phi epsilon is going to be, and then when if so, this reduces to mod of y less than epsilon by 2, and y has to be here, and chi of 1 minus epsilon by 2 b x minus of y, and then this is phi epsilon of y dy. So, as you can see that if my x is, if mod x is less than 1 minus of epsilon, then what we are going to get that this is going to be inside the ball, x minus of y is going to be inside the ball 1 minus epsilon by 2 b. So, that gives me 1, and then the integral of phi is equal to 1. Therefore, the integral of phi epsilon is also going to be 1. So, therefore, if this happens, then phi epsilon of x, this is equal to 1 if mod x is less than 1 minus epsilon. Now, if my mod x is greater than 1 minus epsilon, then this x minus of y, this is going outside the 1 minus epsilon by 2 ball. If mod x is here, then x and y is going to be on this. Therefore, x minus of y is going to lie outside the red ball. So, therefore, this is equal to 0 if mod x is greater than 1. With the similar argument, what one can find exactly in the same way, psi epsilon of x, this is equal to 1 if mod x is less than 1 and is equal to 0 if mod x is greater than 1 plus epsilon. If it is greater than 1 plus epsilon, then x minus of y is going to lie outside this blue ball. So, this is what one can easily compute. Okay, then we know that the estimate of the Fourier transform of the unit ball, and what we can see is that phi epsilon hat, this is equal to chi of 1 minus epsilon by 2 b hat times phi epsilon hat at xi. Now, if we take the modulus, then this is less or equal to, we know the estimate of chi b hat, therefore, we know the estimate of the dilation of the ball. So, which essentially would get some constant times 1 by 1 plus mod xi square to the power n plus 1 by 2 into, and phi epsilon is a Schwarz class function, because it is continuous smooth continuous function with compact support, it is in Schwarz space. So, this what one can get epsilon mod xi to the power n for large n, because of the Schwarz class estimate. Okay, so, similarly we will get the similar kind of estimate for psi epsilon hat of xi, which is less or equal to some other constant c prime for large n. So, and hence what we have got is that summation over m varies over z n, and chi of b, that is the required one which we are talking about, the way we have chosen our phi. So, this is definitely going to be greater or equal to m varies over z n phi epsilon of m by r, and this is a non-negative quantity. So, this is greater or equal to this, and what we have seen is that phi epsilon as well as the phi epsilon hat property, appropriate decay property. So, which we can write this is equal to m varies over z n by the Poisson summation formula phi epsilon hat of, and this is going to be r to the power m into m times r by Poisson summation formula, and this is greater or equal to summation m equal to 0 and then the rest of the thing. So, this is r to the power n mod of phi epsilon hat at 0 and minus summation over m varies over z n minus 0 and r to the power n mod of phi epsilon hat at m r. And this essentially is that if we are writing that the measure volume of the ball, if we take this, then this is and if we take for our purpose epsilon is small, therefore, in particular if we are taking r to the power n, this is equal to epsilon to the power minus of 1. We can choose our epsilon dependent on r such that r to the power n is this. So, this can be the volume of the ball B into 1 minus epsilon to the power n, and this minus of some constant, you will get the decay property of the phi epsilon. This m varies over z n minus of 0, and then this is r to the power n 1 plus r mod m square n plus minus n plus 1 by 2 into 1 plus epsilon r mod m to the power minus of n. So, if we denote this as the number of lattice point n r, then n r what one is by using that 1 minus epsilon to the power n is greater or equal to 1 minus n epsilon. So, what one get is that b, and with this little bit of arithmetic manipulation, what you will get this plus b go of, which is bounded by r n into n minus 1 by n plus 1. So, similarly, if we get we do the exactly the same computation for psi epsilon, we get the other side of inequality for by using psi epsilon, we get n r is less or equal to and this suggests, this gives us a bound for the lattice estimate for the number of the lattice point present in a ball of radius r. So, as you can see that if we are taking for dimension n is equal to 2, then we can get that this lattice point is more or less comparable to pi times r square plus b go of r. Okay. So, that is one nice application of Poisson summation formula, and we will see another application of the Poisson summation formula here. Okay. So, now if I again this is about the counting the lattice point. So, now if I take a symmetric rectangle symmetric around 0 and a rectangle which if symmetric is, if x belongs to S will imply minus of x belongs to S. If my S is a subset of R n is called symmetric. Okay. So, symmetric around 0, that is what is. So, now if I have a rectangle, then I can always safely say that there will exist, if mod the area is greater than 4 in R 2, then definitely this is going to contain some points, integer points, lattice point in this. Now, we can ask this question for any symmetric domain which is a convex domain. So, let S be a convex symmetric domain in R n. So, now the question is, does S contains a lattice point other than 0, other than origin. The Minkowski answered this question by, let us say, the volume of S to be integral over R n chi of S of x dx. That is what is the volume. Now, if we have mod of S is greater than 2 to the power n and indicator function Fourier transform if it has this decay, then Minkowski showed that S contain a lattice point other than the origin. Okay. So, what we will do is the following: define f is equal to indicator function of s by 2, indicator function of s by 2. As you can see that S is a symmetric domain. So, S by 2 is also a symmetric domain. Therefore, f of 0 if we are computing, then this is going to be integral of R n chi of S by 2 of x chi of S by 2 of minus of x dx, which is equal to chi of S by 2 of x square dx, and then this is nothing but this is equal to because this function is 0 and 1, therefore, its square is equal to itself, and this is by our definition is mod s divided by 2 to the power n. And as you can see that the support of f is contained in S, because S by 2 plus S by 2, what we are going to get that it is contained in S. Now, if there is no such k lattice point, in S, then f of k, this is equal to 0 if k belongs to Z n and k is not equal to 0, because this is support of f is sitting inside S. Suppose S does not have any lattice point, then the value of f of k is going to be 0 for non-zero k. Okay. So, now as you can see that f hat of xi, this is equal to and this is a symmetric domain. So, basically this is mod of chi s by 2 hat of xi square. So, therefore, what we get is that f of 0, this is equal to summation over k varies over Z n f of k, and this f hat has an appropriate decay. So, that we can apply the Poisson summation formula for this f, particular f what we have chosen. So, therefore, this is going to be summation over k varies over Z n f hat of k square f hat of k. Now, as you can see that f hat by this observation is a non-negative quantity always, because this is f is chi s by 2 convolved with chi s by 2 tilde, because of the symmetric property of S. Therefore, this is a non-negative quantity. So, this is greater or equal to f hat of 0. Now, what is f hat of 0? F hat of 0 is nothing but in mod integral r n chi of s by 2 of x dx whole to the power square. As we have seen the and this is nothing but integral of r n chi of s by 2 of x dx. What is given to us is that the volume of S is greater than 2 to the power n. Therefore, this volume of S by 2 is definitely is going to be greater than 1, and now this is a contradiction, because left hand side is going to, this one is saying that this is strictly less than 1, the volume of S by 2. So, that is a contradiction. Hence, S will definitely contain a lattice point other than origin. Okay. So, that is another application of the Poisson summation formula, and now we will see some more application of this higher dimension Fourier analysis in the field of science and engineering. So, for further application of this Fourier transform, let us see one application which is very practical and which is which we encounter in our day to day life. So, we do X-ray, we do CT scan, that is the computerized tomography. And so, what does the CT scan it does or X-ray it does? What is the mathematics behind this tomography? So, essentially we can understand that this tomography is a mathematical process of imaging an object via a set of slices. So, what does it happen that I have an object. So, I take I pass through the X-ray here and I get the image, which is essentially a 2-dimensional thing when X is going, and by getting the data from all those X-rays what is passing through, our aim is to reconstruct the image of the object, which is a 3-dimensional thing. That is essentially what is happening in. So, now we can pass on the X-ray by various direction, not only with the parallel to the axis. So, we can get it from various direction and collect all those data, and we would like to reconstruct the 3-dimensional thing. That is basically what we mean by tomography. Now, in the medical imaging or in the tomography, what it happens is that, so what do? We pass on the X-ray. So, it hits the object and then it passes through the object and we get into the other point. So, now there is some this X-ray gets absorbed by the object. So, we have the initial point and the final leaving point, we get that what is the absorption has happened in the object. Now, we capture those absorption. Suppose for example, if you have a bone, then the bone absorbs the maximum and then the soft tissues will absorb less, but various soft tissues will have various level of absorption. So, now the most important thing what we can see in the tomography is the ability of the object to absorb X-rays with given energy. Okay. So, we call this coefficient. So, usually what we take is that so this coefficient is a function. In mathematical term we can understand that it is a function which varies from point to point within the object, and usually we take that which vanishes outside it. Okay. As we have noticed that the bone absorbs the maximum, that is why we can figure out even with a simple X-ray that whether we have fracture or not. And now, if we convert this into a mathematical thing, object, mathematically I will see that a function on R3. Now, R3 means I need to fix a coordinate system. So, work with a fixed coordinate system. So, now fix any one, let us say x3, the third coordinate, and define f on R2 by f of x1, x2 with a constant c is phi of x1, x2, x3. Now, for each of this c we have the information of f c. Now, we need to reconstruct the entire phi, that is loosely speaking is the kind of the problem what we are dealing with. So, now what are the rules we must follow? The object affects intensity of X-ray beam. Let us call this as IS. Where S is the distance of the arc length in which the X-ray beam is passing through the line. So, now, what we want to find is that the change in the intensity changes from S to S plus some change in delta S. So, how it is going to be given? So, this we follow something called a Beer's law, which says that d I, the intensity, by d S, rate of change of the intensity, is nothing but phi of x of I. This is what is the Beer's law says. We have the change in the intensity. So, now our question is that how we are going to reconstruct the object, which is a 3-dimensional function, given the information on the 2 dimension, or for example, if we get it from all the planes when we are doing. So, we have the information of the function which is averaging over the plane, and then from that information we would like to reconstruct the function. So, we will pose this question in a correct mathematical setting, and by using Fourier transform in the higher dimension, here in this case our dimension is 3, we will see that how successfully we can reconstruct the object, or rather we need to find a formula where we can express the f in terms of all those X-ray plate slices, information having in the slices. Thank you.